This video pertains to section 1.2 of your Gilbert text, and it's about the atomic viewpoint of matter. Nobel Prize-winning physicist Richard Feynman once said that if some catastrophe were to destroy all human knowledge, what one idea from science would be the most important to preserve for surviving generations of humans? Well, according to Feynman, it was the notion of atoms. That at its most fundamental, matter in nature is made up of little lumps or particles. So why is this so important? Well, because so much of what we understand today in science is based on this idea. Starting from the notion of atoms, you can explain, well, a whole bunch of stuff. So yeah, this is pretty important stuff, and you'll be using and developing your viewpoint of the atomic world all semester. Every lab, in fact, you'll be asked to draw atomic-level pictures to explain the behavior that you observe in lab. So, what is an atom? Well, here's your textbook's definition. Atom is the smallest bit of an element that still has the chemical characteristics of that element. So, what does it really mean? This gives us a clue, but it's going to take the better part of this semester to really understand what atoms are all about. So what does it really mean to say we still have the chemical characteristics of that element? Certainly one atom won't have the same density as a collection of those atoms. So we're going to need to develop a deeper and more sophisticated understanding of what an atom is as we go along. But this is a good start. So the idea of atoms has really been around for a long time. So the ancient Greeks, and this character right here, Democritus, gets a lot of credit for popularizing this notion of atoms. Well, the ancient Greeks had thought a lot about atoms, and actually they approached it from a philosophical point. So suppose you have a chunk of stuff, and you take that chunk of stuff and you cut it in half. Then you take a half and you cut that in half again, and you cut that in half, and so on and so on and so on. So the Greeks asked, well, what happens? Well, some felt that matter was continuous, and so you could just keep slicing it up smaller and smaller. If you had something small, you could always cut that in half. Reasonably, it makes sense that you should be able to do it. Well, there were some philosophers that argued, no, you get down to some point, and you can no longer cut it. It becomes uncuttable. In fact, the Greek word atomos means uncuttable, and that's where we get our word atom. So there were some Greeks that thought matter was continuous, and some that thought it was atomic. You had to wait a lot longer to really get some solid evidence, rather than just philosophy, some evidence from nature that the atomic idea was right. So this guy, English schoolteacher John Dalton, around 1800, took some evidence that was already known and some of his own experiments with mixtures of gases and came up with an atomic theory that made sense of all that data. So he proposed our first atomic theory. Today we have a lot better evidence that atoms, in fact, are a good model that atoms exist. So we can actually see these atoms using this really fancy technique called scanning tunneling microscopy, STM. So let's look at this little image right here. So what you're looking at here, this little character, was made by the folks at IBM's Almaden Research Center by taking carbon monoxide molecules and putting them down on a metal surface. So if we look here at this guy, each one of these little things that looks like a hill, like right here in his foot or in his hand, that is an individual carbon monoxide molecule. So a carbon monoxide molecule is made up of one carbon atom and one oxygen atom. So each little hill that you're looking at here is two atoms. So you see there's sort of one atom next to it. You see that little bit of bright light? That's the second atom. Together they make up one CO molecule. So this is really pretty cool. So we can actually see or image atoms on the atomic scale. And to give you a better idea of scale, imagine that we had 25,000 of these little guys holding their hands together, making a big long line. That's approximately the population of the town where Illinois College is located. So even if you have 25,000 of these little guys stretching hand to hand, they still wouldn't quite span the width of a human hair. Atoms are really small. So what do I think of when I think of an atom? So the image that I hold in my head is that atoms are made of little balls or spheres. That's what an atom is. So different atoms of different elements are going to have different properties because elements have different properties. Two of those important properties are mass and size. And here you see some different sketches of atoms, different sizes, and their different masses. Notice it's interesting that carbon here has a mass of 12. It's a little bit larger than oxygen here, which has a mass of 16. That's kind of curious. Usually you would think if you have more mass, you're probably going to be bigger in size. That doesn't always happen. We're going to have to wait for a while to really come up with a good explanation, as a good theory as to why that might be the case. So stay tuned. We also know that you can take atoms and stick them together. So two or more atoms can be chemically bonded together to form characteristic units that we call molecules. So here's some examples of molecules. So here we've got two atoms of the same type, two oxygen atoms bonded together. And since it's both one type of atom, this is still an element, not a compound, even though it's made of two atoms. This is what we call a diatomic molecule because it's made of two atoms. So this is oxygen. We give it the formula O2. A little subscript 2 right here. It's just telling us that we have two atoms. So here we have another molecule, and this molecule is made up of two different types of atoms. So this is a compound, not an element. And in this case, we've got two hydrogens, the whites here, and one oxygen. They're bonded together. We can write that as a formula H with a subscript 2O. Now, this is just plain old water, and this is the chemical formula, which tells us how many atoms of each type. So this brings us to the different ways that we can go in and represent molecules. So first, and in its simplest form, this is what most chemists write because it's hard to draw out all these pictures, we use chemical formulas to represent molecules. So a chemical formula will tell you the number and type of each atom in the molecule. And sometimes, in the case of acetic acid here, the formula will even tell you something about how the atoms are put together. We'll see that in a second. So here water has two hydrogens and one oxygen. Here acetic acid has two carbons and 3 + 1, 4 hydrogens, and another 2 oxygens. So we could have written that formula as well as C2H4O2. Here are structural formulas. They show with little lines bonds between the atoms. So they tell us how the atoms are put together in these different ways. And we'll learn about what these lines mean later and why two lines might mean something different than one line. Then we can look at ball and stick models. These ball and stick models show us how the atoms arrange themselves in 3 dimensions, in space. So they tell us more about the shape of the molecule than we can represent here with just a structural formula. Oh, notice how the chemical formula up here and the structural formula up here are kind of related for acetic acid. So the chemical formula says CH3. What's the first grouping of atoms that we come to in the structural formula? Well, it's a carbon bonded to 3 hydrogens, so that's a CH3. Then what comes next? A carbon. So there it is in the formula. Then you've got the 2 oxygens, and finally there's this hydrogen that's attached to an oxygen. So a chemical formula can also sometimes suggest a structural formula. Finally, we have these space-filling models. These give you the idea of if the atoms were to inflate to a giant size, what would the molecule really look like? So it shows you the relative sizes of the atoms. It gives you an idea of what the shape of the molecule might really look like, if you could see one. They're too small to see. One other thing I should point out before I leave this last slide, an important skill that you should be able to do is start with one of these structural formulas or one of these models and reconstruct the chemical formula written in this way for the molecule just by counting atoms. So in this case, if you had said C2H4O2, that would be a correct chemical formula, even if you didn't quite know how to write it out like this. So in a previous video, you learned about elements, compounds, and mixtures. It's important that we have an atomic viewpoint picture of what's going on and what's different between elements, compounds, and mixtures. So here first we have a sample of an element. This is the element helium. Now helium is made up of individual atoms. They don't stick together, bouncing around. So here's an image of helium gas. This is an element because there's only one type of atom present. So this is also a pure substance because there's nothing else mixed in. Here we have another example of a pure substance. In this case, it's a compound. We know it's a compound because we've got 2 different types of atoms, a carbon atom and an oxygen atom. They're bonded here in this way, CO2, to make molecules of carbon dioxide. These molecules of carbon dioxide, little independent guys bouncing around inside this box. So this is another pure sample, but in this case, of a compound. Now here we have a mixture. So we've got different types of atoms, but also different types of substances. So you see here, these 2 blue atoms are hooked together. So those are the same type of atoms. So that's a molecule of an element, right? But then we've got different types of elements mixed in here. So here these white atoms are bonded together. So maybe these are hydrogens, H2. Maybe this is nitrogen, N2. Maybe this is oxygen, O2. So what we've got here is a mixture of different elements. So we've seen here in this example that sometimes you can have elements like O2 that are diatomic. Sometimes you can have elements like helium that are what are called monatomic, just exist as one atom. How do you know the difference between those? How can you remember them? Well, we know the difference between them because we've measured them with experiments. But once we've measured them, then we know them, and we just have to kind of memorize which are monatomic and which are diatomic. So the monatomic elements are a select group of elements called the noble gases: helium, neon, argon, krypton, xenon, and radon. They're easy to remember because if you ever look at a periodic table, they are that rightmost column on the periodic table. So those are all monatomic gases. So they exist as just single atoms floating around. So then there are diatomic elements. Those are Br, I, N, Cl, H, O, and F for bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. And they all exist as diatomics: Br2, Cl2, F2, that kind of thing. Now, some of these are gases, and some of them are liquids like bromine, some of them are solids like iodine, the rest are gases. So how do we remember them? Well, I remember it this way by writing them out so that they spell kind of this German-sounding name, Brinkelhoff. Herr Brinkelhoff, ja? Yeah, so Brinkelhoff. So that's how you can remember the diatomic elements. Now, all of the other elements on the periodic table have more than one atom put together to make the substance under normal atmospheric temperature and pressure conditions. So, for example, sulfur exists as rings of 8 sulfur atoms in one form, so S8. So the other elements are then more complicated.